So last week we already know that the graph traversing can be done with stack and can be done with queue. Today we're going to learn about the breadth first search. Maybe you already know what is the depth first search from the previous slide. The DFS is depth first search, but this one is breadth first search. So it is a general technique for traversing a graph. You still remember what is traversing? Traversing means you want to visit every node in a graph. So in the BFS traversal of a graph G, it means we are going to visit all vertices and edges of G. And we need to determine whether G is connected. It computes the connected components of G and computes a spanning forest of G. So I hope you already understand the concept of connected component, spanning forest, and let's be sure. So BFS on a graph with n vertices and m edges takes O(n) plus m. So if you still remember, this performance is the same with the DFS. And BFS can be further extended to solve other graph problems. So you can use BFS to find the minimum number of edges between two given vertices. And you can also use BFS to find a simple cycle. Okay, so I think you remember what is simple cycle. Now we are going to look at the algorithm. So this algorithm also uses the label. If we use in the DFS, you still remember what are the label? We have visited, okay, and then we have another label about the ads, which is the back ads, okay. So here we have another kind of label for the ads. We call it prospects. Okay, so later we will look at what is the difference between back ads and prospects. The idea of the first part of this algorithm is the same with DFS. At the first time, you will input the G, and then we are going to output the edges and the partition of the vertices of G. So every U in the G, it will be set as unexplored, and every E in the G will be set also unexplored. And then for every V, if the label is unexplored, then let's do the BFS G, B. So this is the algorithm that we will do here. So in the BFS G, S, okay, so S represent the vertex. So S represent this one. We will have L0. We have L0. L0 means this is the list of the 0 level. And then we are going to put the S into the L0. And then we set the S as visited. So the difference with the BFS, we will set the visited after we enter the loop. But in the BFS, we will set the visited whenever we enter into this vertex. And then we will start the I with 0. If Li is not empty. Okay, you understand this one? The meaning by this symbol is negative, not. So if Li is not empty, what is I? I is Q. Okay. Then we know that L0 has one vertex. So it is not empty. Because it is not empty, we enter into this loop. So the Li plus 1, it will be a new empty sequence. It means we are going to make a new list, and for all V in Li elements, because we know that I is 0, so yeah, we will check for every vertex, and for every vertex in Li, we will check the incident edges from that vertex, and then check if the label is unexplored. So if I have one node like this one, if the label of E is unexplored, then let's check the opposite. So let's check the opposite. And then if the label of W, which is this node, is unexplored, then set the label, this one, as discovery. And then set W as visited. This one visited. And then Li plus 1 will be L. It means if I start from 0, now I is 0, then L1 will have a new element, which is W. So if the label of W is not unexplored, so if this node it is already explored, then the label of this edge will be cross or cross edge. So we will repeat this one until we finish to check for all the vertex. So this I will be added by 1 until all the Li is empty. You can see from this implementation, maybe let's look at this Python implementation a little bit later. The idea is the same. Okay. We have the unexplored UV and we have visited vertex. And then this is for the unexplored edge. This is for the discovery edge. And we have another kind of edge, which is cross edge. So let's start with this kind of graph. At the first time, if we start from A, then L0 will be available for A. So A will be the first node, and if you first put all the nodes as unexplored, and maybe the first one is unexplored, so the first A will be visited, and then we will check what is the incident edge of A, and then we will check what is the vertex in the opposite of A, and then if the B is not visited, or if B is unexplored vertex, then we will put visited. So we have the L1, it will be B for the first time. So this L0 means the I, when it is 0, it will have only one vertex, and L1, when we know the opposite of L0, then it will be entered into the L1. And this AB, it will be the discovery X, because it is unexplored. After we have, this is the first, based on the algorithm, we want to find the incident of A, and then we will find another incident X of A. So we go to the C, which is the opposite of A. So C, at the first time, it is unexplored vertex. So we visited C, and then we put the AC as discovery X. And the next, we have the possible incident X, which is after B, and then C, and then D. So we put all of them in the L1. So it is in the list 1, or I can say this is all the nodes after A. So we will explore the B, C, and B, and then all of the edges will be set as DE, or discovery edge. After all the vertex that is opposite of A, it is B, the opposite of A is C, the opposite of A is D. Now we are going to explore when I will be added by 1. So we are going to explore from L1, which is B, because all the vertex from A that has the incident X already finished. Okay. So if you look at the algorithm, for all E, which is the incident X of P, because we already finished this one, then we will go to the next P. Okay. After we have P from the L1, now let's check. This X is unexplored. Okay. The first time it is unexplored. And we are going to find the opposite of B. The opposite of B is C. And C, if you check this one, C is already visited. If C is visited, what happens? So we need to check if the label of W, what is W? W is the opposite of B. So if W is unexplored, then we set discovery. But now the node C is already visited. Then we will go to the else. So to set the label as the cross X. So in this case, we know that C will be visited from A, not C, not visited from B. So here, because we start from B and C is already visited from A, then this X now become this, cross X. So the BC becomes cross S. And then we can continue. We will check the P, which is the another incident X, and this is the opposite of P. Because this is the opposite of P, now we will check. Is it already visited? At the previous one, it is not visited. So we set this one as visited. And then the PE will be the discovery X. After we know that we already checked the incident X, it is this one, and this is the incident X. So we finish with P. After we finish with P, then we will continue to the C. When we continue to the C, again, we want to check the incident X. The incident X of C is this one, and then the opposite of C is D. D is visited or not? D is already visited. Because it is already visited, then this X becomes cross X. So C, D become cross X. And the last one, we want to check from C to the incident X of C, which is this one, and then we want to see the opposite of C, this is F. So F will be set as visited, and because F is not explored previously, so we put the DE for this X. So at the final stage, we already know that all vertex already visited. So the BFS finish, and then this is the final stage of BFS. The last one, because we have only DF and F already visited, so this X will be the cross X because F already visited. So when we have the BFS, the spanning tree will be this one. This will be the spanning tree based on the BFS. So in the BFS, we know that we have G. It is the connected component of S. So the connected component means every node is connected. And then the property of the BFS, the property one means the BFS GS will visit all vertices and edges of the GS. So every X, every vertex will be visited. And then the property two, the discovery X labeled by BFS form a spanning tree. So this is spanning tree. Okay. The discovery X is the spanning tree. The cross X is not included in the spanning tree. Okay. The property tree means for each vertex V in Li, so we have this Li. Li when I equals to 0, this is a set of vertex. When I equals to 1, this is the set of vertex. And then when L equals to 2, this is the set of vertex. So for each vertex V in Li, the path of TS from S to V has I edges. What does it mean? The path from TS from S to V. So if S is the starting, then from S to L1, there will be one edge. Here, there will be one edge. Here, there will be one edge. But if we have the Li equals to 2, then there will be 1, 2 from the starting point. If we go to F, then there will be 1, 2 from the starting point. That's the meaning of this one. Every path from S to V in GS has at least I edges. So it's the same with the property 1. So the analysis of this one, we are going to set the label of the vertex and edge at the first time. So it takes O1 time, just setting the vertex and the edge, whether it is unexplored. And each vertex is visited twice, because we have the vertex V, we visit V, and then we want to check the opposite. The opposite of V is W. So we will visit first is unexplored, and the second we want to find the visited. And the edge will be also labeled twice. The first is unexplored, and the other is either discovery or prospects. Each vertex is inserted once in the sequence of Li. So if it is L0, we have A. If it is L1, we have B, we have C and D. For L2, we have E and F. So every vertex will be only in one L. So the method incident edges is called once for each vertex. So if I'm now in the A, then I will check what is the incident edge of A, what is the incident of A, what is the incident edge of A. So every edge will be, every vertex we will call once. And then the BFS runs in ON plus M, provided the graph is represented by adjacency list. You still remember the adjacency list? Okay, in the graph we have three kinds of lists: edge list, adjacency list, and the adjacency matrix. Okay, so that's the basic one for the graph. And we have one properties. So the number of edges 2 multiplied by m will be equal to the summation of the degree of the vertex. So this is the graph property. So there are many applications for the BFS. Using the template method pattern, we can specialize the BFS driver law of a graph G to solve the following problem in ON plus M time. For example, I want to know the connected component of G. Or I want to compute a spanning forest of G. So I want to know how many forests or how many trees that I have in the forest. Or I can find the simple cycle in G. Or if I want to report whether G is a forest. If I have two vertices, given two vertices of G, find a path in G between them and find the minimum number of edges, or report that no such path exists. So with this BFS, you can do the short path problem. So this is the summary. What is the proper application for both of the method that you already learned. In the DFS and BFS, we can use it for the spanning forest, we can use it for connected components, we can use it for pets, we can use it for cycles. But yeah, the BFS is more proper for the shortest path problem. DFS is more proper for bi-connected components. So in the DFS, you can see I have this A and then I will connect to B, C. Okay, I can have like this spanning tree. But for this BFS, this is for the BFS, you will have the L0, L1, and L2. And this L indicate that you can find the shortest path by finding the edge, by finding the edge or the nearby edge, and then you can calculate the cost. So the difference between the BFS and DFS is the back edge and the cross edge. If it is the back edge, so it is the DFS, and we call W is an ancestor of V in the tree of discovery edge. You still remember ancestor? The ancestor means if I know E, it is a node, then C is the ancestor. If I know C is the current node, I know that B is the ancestor. So the ancestor means the path. But if I know E, the current node is E, so B will be the grandparent. A will be the grandparent of B. So we got this is the ancestor. If we use the BFS, we have the cross edge. So W is in the same level as V or in the next level. For example, if I start from A, then B, C, and D will be in the next level. So if it is 0, then B, C, and D will be in the level 1 or level +1. Or if now I'm in the current node, this is B, so there will be the same level of B. So with this C or B. So that's the meaning by the process. Okay, so let's look at the code. So I already give you the graph example. I will run for all the code. Okay, so you know about the graph. I give you the graph example for this graph, and then you already learned about the incoming and outgoing. Now let's look at the depth persons. So this is the code given by the book that I use for the reference. So we have the G, which is the graph, and then U is the vertex, and then discover is the mapping. Okay. It is the map whether the node has been discovered or not. So we can construct a path. So U and V are the nodes, and then we want to check whether it is already discovered or not. So in the construct path, we have the path which is empty. So if V is already in discover, so we can construct a path. So path will be added. So V will be added into the path. And then now we will walk from V. And then if walk is not U, because I'm going to, let's say I'm going to start from U and I'm going to go to V. So for the V, if walk is not in U, then we will discover for every node and we will put it into the S. So, oh, sorry. So this is the S that leading to the walk. And then we are going to check if we have this E, what is the opposite of this V? And then we want to put this parent as one of the node in the path. Okay. We know that in the in the DFS, the concept is the ancestor. So the ancestor means the parent. If we can find the parent of that node, then we will put that node into the path. So after we have all the path, we will reverse it because we start from V. So we actually we want to know from U to V, but this is from V, and then let's check the parent, and then let's check the parent, let's check the parent until we go to U. Then because we are already find all the path from V to U, so we are going to reverse it. So the reverse will be from U to this node and then go to the another node and then go to V. That's the meaning by this reverse. In the DFS, we can use this one. This is the DFS complete. So the forest will be started with empty dictionary. If U is in the vertices, so if U is not in the forest, then forest U equals to null. And then we will do the DFS, G, U, forest. Then we know that we will do this one. So if I run this, I'm going to use the graph Korea. So last time we already learned about one example of the graph, which is the graph Korea. Yeah, this is the example that I give to you. So this is the graph, and I want to find the spanning tree. Okay. So using the DFS, I will input the graph Korea, and then I can get the incoming from this DFS. So I can check what are the items in the graph Korea. So these are the items that has been discovered, and this is the spanning tree that we can get from the DFS. So this is the graph 1, and this is the spanning tree from the graph 1, and this is using the graph 2. This is the spanning tree from the graph 2 using DFS. For the breadth first search, this is from the book. The idea is the same. We have the G, which is the graph, and then S is the starting point. So we learn for every step in the slide. So they provide the level. So the level, if the level length is higher than 0, then we will do this one. So you already know the code that we already did step by step. And then the BFS complete is similar to the DFS complete. We want to put every node as undiscovered or unexplored. So the same idea with the DFS, we can put the graph into the BFS, and then we can make the spanning tree. The graph one we can put into the BFS, and then we can find the spanning tree. And we can put the graph 2 into the graph, and we can make the spanning tree. Okay. Now, I'm going to teach you how we can do a kind of random. So I know there are some people, some teams who do the graph. Okay. So I'm giving you a code how you can create the graph randomly. So there's a package. I use the network X. Okay, so this package is good for the graph. So if you don't have the package in your computer, please install it in your Anaconda. Okay. But I guess now Anaconda provides this library. So using the network X, I would like to make a random graph. So it is, I will provide the N, which is the nodes or the vertex, and M is the edges. Let's say I'm going to make a random node for 10, and then I'm going to make edges for 30. So I would like to make the random graph with this function, and then I'm going to put the X list, okay, in this file. Okay, so this is a file, okay, that you will write all those one. And now let's you can make in the file, or you can just make into a list. Okay. So if you have the list, this one. So if you make a file, then you will see this kind of file. So G1 dot at s 0,5, G1 at s 0,9, and so on. So it is random. So you have 10 nodes, and you are going to create 30 edges. You can make with this file, or you can make with a list. Okay, so I'm going to put into the list. And let's say I'm going to put all the lists into a tuple. So you know what is the difference between tuple and list? List is modifiable. You can modify the content. But tuple, it is not able to modify, or it is immutable. Whenever you do with the graph, I think it's better to put into a tuple, because whenever you do some kind of calculation, the nodes should be fixed. Okay. Then people would like to use tuple because it is not modifiable. Now, let's create this kind of edges. You know, this is the edges. And because this is the edges, we can use the edge, please. You still remember? In the first part of our example, here, we can make the graph from the edge list. So I'm going to use the edge list to create this graph. Okay, so I'm going to use the graph from edge list, and the data is LL tuple. The data is this one. And then, yeah, I put this directed graph is true. So in chapter 3, we learned how to calculate the running time. So this is the code, but let me show you how we can create the running time. If the data is small, I think the running time will be 0. So I'm going to increase the number of nodes and the number of edges. Now I put the number of nodes is 100 and the number of edges is 300. So I make another graph which is T100. So it means the graph with 100 nodes. And I put the node into a list, and then I create the edge and I make it as a tuple. And then I create the graph from edge list. Now I want to make another graph which is G1000. So G1000 is a graph with 1000 nodes and 3000 edges. And then I have another. Oh, okay. Let me just use the time performance. So the time performance means I want to check for every code that I have, and I want to use the DFS. So the first time I'm going to put the start time, and then I'm going to put the end time, and in the middle, let's run the algorithm. So the algorithm, if it is in the middle, then I can see that the end time minus the start time will be the elapsed time. So I can get this elapsed time for the algorithm. Now let's look at this one. I already have the graph Korea, graph random 1, graph random 2, and graph random 3. Okay, so this is the graph random 3, this is the graph random 02, and this is the graph random 01. So using this one, I'm going to check what is the running time. So the running time for the graph Korea will be in the T1. The running time for graph random 01 will be in the T2, and so on. So we will have T1, T2, T3, and T4. So for example, I have the T4 is this one, 0.004. So if the number of nodes is getting higher, then the time will be slower. Now let me check if I put 10,000 nodes and 30,000 edges. So I have the graph random 04, and let me again do the runtime. So it is 0.03 second. So it is a little bit slow because we have many nodes. After you have this one, then let's put all the time into one list. So I'm going to put the T1 into the test DFS. I'm going to put the T2, T3, T4, T5 using the append function. So I will have the test DFS. It is a collection of the running time. And after this one, let's look at the BFS. So I will run the S1, S2, S3, S4, S5, and then I do the same for the BFS. I will add the time into the BFS, and then if you check BFS, so this is the time of the BFS. So after getting the runtime for both DFS and BFS, we can plot and compare the time performance. So in this case, we have X is 5, 10, 100, 1000, and 10,000. So this represents the number of nodes. We know that the graph Korea, we have only 5. And then the first random graph is 10, the second random graph is 100, the third random graph is 1000, and the last random graph we have 10,000 nodes. So we put this as X. Okay, so this is the test DFS, and then we can plot it. So this is the plotting time for the DFS. So you can see that if it is 0, or if the first data is 5, yeah, it is nearby 0. But when the nodes is 10,000, then it reaches 0.03. We can compare with the BFS. So we can just put the, in this case, we have the label, which is the data, and then we have the Y label, which is the time, and the title is DFS. So we are going to plotting the X, which is this one, and plotting the test DFS. So it is the time for every of the point. We want to put all the nodes in the red color. So this is red color, okay, RO. And we are going to show. So we have the, actually the color can be specified. You can specify in the red, and you can specify in the blue. And then here we can plot both DFS and BFS, and then the legend will be based on the sequence. So because this is the first, then DFS will be the first, and this is the second, then BFS will be the second. So you can see that DFS and BFS runs in almost similar performance. Okay. So at the end of your field project, you need to show this one. You need to show the time performance. So if your data is small, no problem, you can create random, right? What I mentioned in this example. So in the conclusion, the time performance is BFS. Okay, it depends on how many times you do the experiment. Okay, because I did once, so BFS is slightly higher than BFS. Yeah, it depends on your computer, whether your computer is running many other programs. If it runs many other programs, maybe some of the algorithms will get slower. So in this case, because I'm using this PC, okay, so you can specify in the academic, in the non-moon, usually they specify what kind of environment that you use to do the experiment. For example, if I use a laptop with the i5 and 16 gigabyte RAM. So if you specify this one, people will know that, okay, maybe because of the laptop specification, the result can happen like this. Or if you use PC, then the result will be different. Okay. And last one, please don't forget that for every algorithm that you did, you need to analyze the big O. Okay. Okay, it's exit time. Let's have a break. Okay, I will continue after the break.